Okay, hello everyone and welcome back to Physics 3150. Last lecture we started talking about sequential circuit and we said that in this basically for digital logic design we have two categories of circuits. We have combinational logic design where we had gates such as AND gates, OR gates, XOR and whatnot. And well, in addition to that, we had arithmetic logic like adders, subtractors, comparators, and we had basically multiplexers and so on and so forth. The common thing between all of these different kind of logic gates was that their output only depended on the inputs, right? And then last time we started talking about sequential logic, where the output is a function of inputs and previous output, let's say. So it had a sense of time, a sense of memory. It remembered what was the previous output. An AND gate doesn't remember what is the previous output. It like basically it only has four. It can only take four different kind of inputs. So two input AND gate, and it just generally it generates the output based on those inputs, and it doesn't care what was the previous output, a 1 or a 0. Okay, but then for the sequential logic design, we learned that we could have gates such as latches and flip-flops that their output depends on their previous output as well. For example, the last thing we talked about was the flip-flops that had reset and set as well. And the truth table or the transition table for this block was if this is D and this is Q, we knew that if D is 0, or maybe we shouldn't just draw the transition table for this. We can just say Q is equal to D at the pause edge of the clock. So we learned that we have D latches where Q is equal to D when the clock is 1, and we have the flip-flops where Q is equal to the value of D at the positive edge of the clock. And we talked about we can have a negative edge flip-flop as well. So we're going to continue our discussions in this line, and well, in the beginning I'm going to start introducing you to another type of flip-flop, which we call them toggle flip-flop or T flip-flop. So we have T flip-flop or toggle flip-flop, which has a symbol that is very similar to D flip-flops. I'm not going to draw the reset and set. You can imagine they're there if we need them. And the idea is actually a little bit different. So with D flip-flops, this was really the principle of operation for them. Q is equal to D at the positive edge of the clock. For the T flip-flops, I can say that Q is equal to, depending on value of T, Q could be the previous value of Q. So QT plus 1 is going to be QT or Q bar T. So if T is 0, if the input is 0, your output is not going to change. If the input is 1, your output is going to toggle. It's going to go to its not, right? So nothing too complicated. It's just a new kind of flip-flop. Before actually, it's a very useful flip-flop, and before we actually talk about how to make circuits using this flip-flop or how to make useful systems using this flip-flop, you might actually wonder how do I make this kind of flip-flop. So we learned how to make D flip-flop using NOR gates, right? We saw that we can use NOR gates or NAND gates and make a D latch, and if I put two D latches cascaded with each other with complement clocks, clock signals, you will get a D flip-flop. Now, if I want to implement a T flip-flop with this kind of principle of operation table or transition table, what I can say is that, let's say I have a D flip-flop and I want to make it a T flip-flop. So let's say this is my D flip-flop clock. And what I know is that for a D flip-flop at the positive edge of the clock, Q is going to be equal to D. So if I make sure that what I put here at T plus 1 at the positive edge of the clock is Q or Q bar depending on the input T, then I'm good, right? So generally, here's my input T. I wanted to go to a certain logic here, and I want Q or Q bar to come out of it if T is 0 or it's 1. Because if I manage to have that, then, well, the next Q is going to be Q or Q bar, like the previous Q or Q bar, right? Well, to make sure of that, first of all, I need to have access to Q, right? So the first thing I need to do is to actually feed back this Q and bring it here. Now, how do I make that logic with T? Well, if you remember, we said that XOR has a very interesting property. We said that if I XOR a signal with a 0, I'm going to get the signal X. And if I XOR the signal with a 1, I'm going to get X bar. Okay, so I want to get a Q and Q bar. So X is really my Q, and T is really my 0 or 1. So if I just XOR these two signals and feed that to a D flip-flop, I can draw a line around this whole thing. So let's say that this is my Q output. I can draw a line here and that would be my T input, that would be my clock, that would be my Q. So I just made a, like the orange box, or well, the contour is basically my T flip-flop. So a T goes in and I have an internal feedback system with a D flip-flop and an XOR. If T is equal to 0, if here I have a T equal to 0, what happens is that this Q here is going to be coming here, right? If T is 1, then I'm going to have Q bar coming here, right? So the Q is going to be complemented, and at the input of my D flip-flop, I'm going to have Q or Q bar, and at the next positive edge of the clock, one of these two are going to be my next Q. So that's how I make a toggle flip-flop using a D flip-flop. Okay, now let's make a useful circuit out of this. So let's say that I have 3 of these T flip-flops cascaded with each other. Now, so this is T, Q, clock. They all are edge triggered, so I have to put that little triangle there. T and Q. Now, what I do is that I connect the first one, the input of the first one, to a 1. And I connect that 1 to the input of the other guys as well. Also, same as set and reset that we don't always show them, you remember even with D flip-flop we had the same thing, so with T flip-flop we do have this. We always have this Q bar here that we always have it. If we need to, we use it. If we don't, we don't. So just go back and look at how we made SR latches and D latches, and you remember that we did have this Q and Q bar all the time. So I'm going to connect the Q bar of the first one to the clock of next one, and the Q bar of the second one to the clock of third one. And I'm going to call the output of the first one Q0, this one Q1, and this one Q2. Okay, so this one has a Q bar, I just don't use it. It's not connected to anything. Okay. Now let's say that this is, and then the input of the clock of the first one, I'm just going to connect it to some clock signal. some square wave kind of a thing. So let's say that this is my clock. So I'm going to do 7, 8 cycles. 3, 4, 5, 6, and 7. Let's do a couple more. Okay. And so this is clock. And let's say I want to draw a couple of outputs, all of these outputs. So Q0. And I want to show Q0 bar because we're going to look at it. Q1, Q1 bar, and Q2. We don't care too much about the Q2 bar at this point. Okay, so initially, let's assume that all of them are at 0. So Q0 is at 0, Q1 is at 0, Q2 is at 0. Therefore, Q0 bar is going to be at 1, Q1 bar is at 1, and Q2 bar, well, we are not really showing it. So let's try to actually go through the operation of this circuit and see how Q0, Q1, and Q2 change over the time. So initially, all three of them are 0. Now, knowing that the input to my to all my flip-flops is 1, and knowing that the property of T flip-flop, that basically the output toggles every time if the input is 1. And then, well, now we know that the input is always 1, right? So this is telling me that, so input of all T flip-flops are 1. So their output toggles at the positive edge of their clock signals. So why did I say their clock signals or not the clock signal? Because their clocks are actually different. The first one, the clock is actually the clock signal. The second one, so it's this guy basically. For the second one, Q bar of the first one is its clock signal. So the positive edge might actually happen at a different time, and we will see that it does happen at other times. And then, well, the same thing for the third one. So let's actually try to see what will happen. So at the first positive edge of the clock, what happens is that for the first one, Q0 is going to toggle, right? So at this positive edge, I know that the flip-flop number 1, so this is number 1, this is number 2, this is number 3. The flip-flop number 1 is going to have its output toggled, right? That means that the Q bar is going to go from 1 to 0. Okay, and this is going to be the output until the next positive edge of the clock, right? How about the second flip-flop? Well, for the second flip-flop, the clock signal, which is here, is really the Q bar of the first one. Well, looking at the Q bar of the first flip-flop, which is Q0 bar, there's no positive edge yet. So what happens is that the Q1 is just going to stay the same, meaning that Q1 bar is going to stay the same. If Q1 bar is staying the same, that means that the clock of the third one is going to be the same, so Q2 is going to stay the same. So nothing is going to change in their world. Great. What's going to happen at the next positive edge of the clock? Well, next positive edge of the clock, Q0 is going to come back to 0, right? And that means that the Q0 bar is going to go to 1. Well, this means that it looks like that Q0 is going to basically toggle, and we know that, right? At the positive edge of the clock, at here, 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 we can see the pattern that at every positive edge of the clock, Q0 is toggling. So let's just actually draw that until the end. So nothing here is going to change. And knowing that Q0 bar is just always the complement or the knot of Q0, I can draw that as well. Okay. Now, the next thing is, well, this Q0, having this Q0 bar waveform is going to help us draw Q1, because this is really the clock of TFF2, the second T flip-flop. So I only care about the positive edges of this one, and I know that my second flip-flop output is going to change or toggle at the positive edge of this waveform. Okay, so this means that I'm going to get a toggle here, a toggle here, toggle there, toggle here, and nothing else anymore. And similar to Q0, Q1 bar is just going to be not of Q1. Last but not least, we're going to talk about Q2, right? So Q2, well, Q1 bar is the clock of the third flip-flop, so I'm going to care about the positive edge of Q1 bar. So Q2 is going to change from 0 to 1 here, and from 1 to 0 at this point. Okay, now that I have all of my waveforms, let's say that somebody is interested to know what is the value of Q2, Q1, and Q0. Like if I have a 3-bit number, Q, which is equal to Q2, Q1, Q0, what would be that number during over this time? Well, let's start with the beginning. The beginning, I have a 0 for Q0, Q0 for Q1, and 0 for Q2. After the first clock at this point, I'm going to get a 1, still 0, still a 0. Now, well, should have actually drawn this here. So a 0, a 1, a 0, a 0. Next clock cycle, so here, I'm going to get a 0, a 1, a 0. Next clock cycle, here, I'm going to have a 1, a 1, a 0. Then a 0, 0, 1. 1, 0, 1. 0, 1, 1. And then 1, 1, 1. And then I go back to 0, 0, 0. So if I read these numbers from bottom to top, because this is Q2, this is Q1, and this is Q0, right? So I have to, if this one is the most significant bit, then I'm starting with a 0, 0, 0, that's a 0, then a 0, 0, 1, a 2, a 3, 0, 1, 1, a 4, 1, 0, 0, all the way to 7. The moment I get to 7, the next clock cycle I go back to 0. So it looks like my Q2, Q1, Q0 start from 0, 0, 0, then it goes to 0, 0, 1, all the way to 1, 1, 1, and then back to 0, 0, 0. Or in the decimal world, I'm going from 0 to 1 to 2 to 3, and all the way to 7, and then back to 0. So you can all see that clearly this is a counter. Basically, as long as I have 3 T flip-flops connected in this way, what will happen is that basically, and as long as I keep the input of all of them equal to 1, and I have a clock like this, then what will happen is that I'm going to get an output that is basically counting from 0 to 7 and then come back to 0 and count again up to 7. Now you can imagine that if I continue this kind of structure and add more and more flip-flops here and here and here, what will happen is that I'm going to get a 4-bit counter which counts up to 15, and then with 5-bit I can count up to 32, up to 64, and this is double. Like basically with 10 I cannot count up to 1,000, and with 20 I cannot count up to 1,000,000. So you can easily count have a counter that basically counts up as much as you want, and depending on the maximum number that you want to go, you can use this counter. Now you can see that the beauty of this reset kind of thing. So imagine that you want to only count up to, so because these things can count up to a number that is a power of 2, right? 32, 64, 128, 256, 512, and so on and so forth. But then let's say you only want to count to 500, right? So not until 512. So you want to go to 500 back to 0. How do you do that? Well, you have to somehow detect that you have reached the 500, and we're going to learn that in, well, next lecture. And then once you have, and you can think of it yourself, and it's not really hard to actually make that detector, but you can detect that we have reached to this 500. The moment that you detect that, your detector block sends a reset signal to the reset of all of these T flip-flops, and they all reset to 0. Okay, so that's how you actually make sure that this thing is actually counting to an arbitrary number that you want. Okay, so in the previous slide we talked about a counter that used T flip-flop, sorry, and basically we built this using 3 T flip-flops. The problem that people generally have with that kind of counter that is, well, less used than this one that I'm going to discuss now, is that the clock of each of these flip-flops is really coming from an output of the previous flip-flop. This causes a lot of issues in terms of synchronization, because generally you want all of these flip-flops to generate their outputs at the same time. What happens with this kind of scenario is that if the delay of this guy is actually smaller than the delay of this flip-flop, or longer than the delay of that flip-flop, you are counting from 000 to, for example, 001, 010, 011. But then what is really happening, or like then after that 100, what is really happening is that you want, like when you go from 011 to 100, from a 3 to 4, what you really want to happen is that you want to make sure that this 1 goes to 0, and this 1 goes to 0, and this 0 goes to 1 at this exact same time. Because if they don't happen exactly at the same time, you might actually, eventually after some time, you might actually get to 100. But then imagine that, let's say these two are happening sooner than this guy. Then you actually go from 011 to 000, then that Q2 becomes 1 and you get to this, right? And then if you have connected this counter output to something, for a second, or like not a second, for a moment of time, your output, or like basically your output of the counter that is going to be connected to the input of some other thing, is going to be 000. And if this input 000 is going to, this could cause a problem. Remember, like for example, for ADC, for building an ADC, if you remember the dual slope ADCs, we actually used the counter and we counted things, and then basically sometimes if we reached a certain number, we wanted to stop the counting. Now, if we imagine that, like going from 0 1 to 100, right? Imagine that the 0 to 1 transition, the Q2 transition, happening sooner than the 1 to 0 transitions of Q1 and Q0, right? What will happen is that I'm going to get a 1 1 1, and then these two are going to go to 0, and I'm going to get a 1 0 0. And then imagine that the next block that you have, the output of your counter, is connected to a block that you have designed that block in a way that if you get a 1 1 1, you start some other, that 1 1 1 triggers some other operation. And then, well, in reality, you haven't actually reached the 1 1 1, but your next block is going to think that you have reached it. Because of these kind of problems, we really want a counter that is fully synchronized. The way that I have to, the way I design this counter is that I still use 3 toggle flip-flops because, well, it's a 3-bit number, so probably I don't need more than that. But I connect the clock signal of all of them to the same thing, so the positive edge of all of them happen exactly at the same time, so they're fully synchronized. Now, if I do this and I connect the input of all of them to 1, then I'm not going to get the right numbers, because I'm starting with 000 at the positive edge of the clock, because the clock of all of them are the same. I'm going to get a 1 1 1 and then a 000, and it's not going to be working like a counter unless I add some other logic gates. Okay, so how do I add those logic gates? Well, let's think about it. To do that, I have to actually think a little bit about the process of counting. Let's say that this is Q2, this is Q1, this is Q0. I want to go from 0, 0, 0 to 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And the moment this happened, I want to come back to all the way to back to 0, 0, 0. Now, if I want this to happen, I have to think about each of these bits separately because each of them is the output of one of the flip-flops, and think about how do they actually change over the time, and then how should be the input of each of these T flip-flops to ensure that that pattern is going to be generated at the output. Okay, so I want you guys to actually pause the video right now and think about what you should actually connect to the input of these T flip-flops in a way that you actually get those Q0, Q1, and Q2. Just to give you a hint, looking at Q0, I can solve one of them for you and you can think about the other two. Looking at Q0, I can see that at every clock cycle, it actually toggles. So the least significant bit actually toggles at every clock cycle. Therefore, I can just simply connect the T to 1, and Q0 is going to be correct all the time. I'm going to get a 0, a 1, a 0, a 1, a 0, a 1, and that's always true. Okay, so but then how about Q1? How about Q2? How do I actually, what do I connect to Q1 and Q2 or to the second and third flip-flop input to actually get to get that behavior? Okay, pause the video and then resume when you were done thinking. Okay, so I hope that you all have thought about this. So the observation that I make here is that for Q1, I can see that whenever it actually changes every 2 rows, right? But I can't count to 2. If I could count, then I didn't need a counter, right? So I have to make a detection. I can see that it actually, the value toggles here, 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 and then, well, the end. So like this goes really, if I want to write this 0, 0, 0 here, this goes to 0, 0, 0. Okay? So I can see that whenever Q0 becomes 1, for the next row I have a toggling. Okay, so it means that my Q1 becomes Q1 toggles at the positive edge of the clock if, and that's the important thing, Q0 is 1. The current Q0 is 1. How do I make sure that both of these are happening? Well, both, like that statement kind of implies an AND operation. So basically we're saying that if the Q1 is actually 1, this thing toggles. Okay, so I can just simply connect Q0 to the input of the second flip-flop. So this is first, second, third. So this way, if Q0 is actually 0, the input of the second flip-flop is going to be 0, and I'm going to hold on to my output. So Q1 is not going to change. If Q0 is 1, then Q1 is going to change. Great. So that kind of solved the problem. How about Q2? Well, looking at Q2, I can see that again, every 4 rows I'm going to have a toggle. So I have one toggling here and one here in the end. So when does that happen? Well, again, if I make an observation, I can see that it happens when both of Q0 and Q1 become 1. When I get a 1, 1, then the Q2 is going to toggle. A 1, 1 implies an AND gate. So when Q1 is 1 and Q0 is 1, I'm going to get Q2 change. And you can continue this process. So if I had a 4-bit counter, I needed to toggle Q3. So like if I had another thing here, Q3, and this was T3, the clock was connected to this again. I still needed an AND gate, and if if you actually look at it, the only toggling happens when I go from 7 to 8. So when I'm from 0, 1, 1, 1 to 1, 0, 0, 0. So I'm going from 7 to 8, or I'm going from 15 to 0 again. So from 1, 1, 1, 1 to 0, 0, 0, 0. So 15 back to 0, right? For both these cases, all first three bits are actually 1. That's when the toggling happens, right? So all I need to do is to put an AND gate and then say whenever Q2 is 1, and I don't need to bring Q0 and Q1, I can just bring AND of them, because AND of the two ANDed with Q2 is almost like a three input AND gate, okay? And I can just basically continue this to as many number of bits as I want. So now this is a synchronized counter, okay? Now, let's say this is my 4-bit counter. So Q0 is here, Q1 is here, Q2 is here, and Q3 is here. Let's do the thing that I promised you to do next lecture. Let's say that, well, I know that this 4-bit counter counts up to 50, right? And then goes back to 0. What if I wanted to go up to 10? Well, if I wanted to go up to 10, I say, well, what is 10? 10 in the decimal is going to be equal to a 1010. Basically, what I'm saying is that whenever you detected a 1010, you want to go back to 0. Well, it's not that hard to do it. So I would say, so this is a Q3, Q2, Q1, Q0. So I'm saying that when Q3 is 1 and Q1 is 1 and Q2 bar is 1, so Q2 is 0 and Q0 is 0, so Q0 naught is 1. So when all of these are 1 and only in that moment, nothing else, right? If I AND all of these signals together, then I know that whenever this becomes 1, then I have reached 10, right? If that happens, then I reset this thing. So that is how you make a counter that counts only up to 10, right? And you can choose, this 10 was an arbitrary number. You can choose any number, any other number that you like, okay? Now you might actually think, well, when set becomes actually relevant, because reset, yeah, I get it. You always want to go to 0, 0, 0, but how about 1, 1, 1? Well, if you Google, it's not really hard, or you can actually think about it yourself, or it's not really hard if you think about it. You can actually design a down counter. You can design a counter in a way that it actually goes all the way from 1, 1, 1, 1 to, well, 1, 1, 1, 1, 0, and then 1, 1, 0, 1, and then you can imagine beyond that. So it goes from 15 to 14 to 13 to 12 to 11 and so on and so forth. So now if you want to reset that down counter, then you can easily do that by basically detecting whatever number that you want to stop, and then setting all of the flip-flops to output 1 once that number is detected. It gets actually more interesting. You can actually design things that are called up-down counter, that you have a counter that it has 2 modes. So if you actually have a control signal that comes in that sets the multiplexer, like you have a multiplexer at the input of each flip-flop, and then based on that multiplexer you're going to be counting up or down. I actually might give you the circuit for that in one of your assignments. Okay, the last thing we want to talk about today is kind of going to be a segue to our discussions for the next week. It's basically a system that is what we will discuss next week are systems that have both combinational and sequential logic in themselves, in their structure. And this example is going to be like a good motivation to do that, right? To actually give you an idea why do we need such systems. Let's say that somebody think about a smart way of actually making a counter and says that I don't need really your flip-flops because I have an adder. You want a 4-bit counter? I take a 4-bit adder. So let's say this is an adder, and it gets two numbers, A3, A2, A1, A0, and B3, B2, B1, and B0. And it just adds them together, right? And it gives me a 4-bit number S3, S2, S1, and S0. And this person is telling me that instead of actually needing flip-flops and stuff, I know that every time that I have a new number, when I'm counting up, I'm basically adding my previous number by 1, right? So if I make one of my numbers 1, meaning 0, 0, 0, 1, and connect the output to the input, meaning that S0 is connected to B0, S1 is connected to B1, S2 is connected to B2, and S3 is connected to B3. So whenever I have this dot, it means connection. So these are not connection. So now, does this work? Because it looks like it works, because basically I have a number B3, B2, B1, B0, and I'm adding it by 1 every time. And I get my output, and I provide my input, and I provide that to my second input. So I start from, let's say I reset this to 0, 0, 0, 0. The next output is going to be 0, 0, 0, 1, and then 0, 0, 1, 0, all the way to 1, 1, 1, 1. And then let's say I don't care too much about the overflow. I'm going to put an overflow detector that whenever you got 1, 1, 1, 1, whenever like the outputs are 1, so just adding all of the outputs together, reset this adder to 0, 0, 0, 0. Okay? So don't worry too much about the overflow detector. The question is that does this circuit work or not? Really, like is it okay to have this circuit? Can you use this as a counter anywhere or not? And the answer, you can sense from my tone that the answer is no, but then the question is, well, why not, right? Again, I encourage you guys to pause the video at this point, think about it for 30 seconds, and then come back to talk about it together. Okay, so I'm hoping that all of you have thought about it, and I'm hoping that you have a guess why not this is working. The reason that I have for this not being a good counter is that it doesn't really have a sense of time. What do I mean by that? Well, imagine I start from 0, 0, 0, 0. When do I go from 0 to 1, from 1 to 2, from 2 to 3, and all the way to 15? Well, how long it takes to actually count up? Because with the flip-flops, I only went from one number to another number at the positive edge of the clock. And then I could, by changing the frequency of that clock, I could actually slow down or speed up these transitions, right? So I could make it every second or every millisecond or a microsecond, but I had a very good control on these transitions. What is really happening with this counter is that I don't have any control on the timing of this thing. So the moment I have 0, if I assume that this adder is actually working basically with a very small delay, let's say 1 nanosecond of delay, a nanosecond later I have this 1, and then a nanosecond later I have 2 and 3 and all the way to 15. So, well, you might want to count that fast, but if you don't, you really don't have any control on things, right? You really don't have any control on how things are actually happening and how fast or how slow you're counting. That's one problem. It becomes more serious of a problem when you think about the internal circuit of an adder. All of these bits are not actually calculated at the same time. So you get S0 first, then S1, then S2, then S3. So by going again, the problem of asynchronous counter that we had, the first counter that we had, if imagine that I have a number 1 0, or like, let's say I'm going from 0 0 1 1, which is a 3 to 4 0 1 0 0, right? If the Q0, this one, happens first, and then this one happens, and then this one happens, I'm gonna have so many wrong numbers in between until I get this. And then those numbers, if this is basically, if one of them is happening in 500 picosecond, the other one is happening in 600 picosecond, and the other one is at 1 nanosecond, then what happens is that every 2 transitions of the first bit, I'm gonna have 1 transition of the second bit. And the delays might actually be that different. So my counter is gonna be basically outputting gibberish to me. It's not gonna be actually working, and not only I don't have any control on the timing of these transitions, the output is not reliable anymore. So how do I actually fix this? Well, the idea to fix this is actually to gate this connection, this feedback connection. Imagine I could have a bunch of switches here that basically, imagine these wires were not connected. I had switches, and only when I send a command, and when this became 1, I actually connected the outputs to the second input. Then when this, like, generally I connect this command to 0, and at every time that I want to, let's say I want to actually make a transition every millisecond I make this command equal to 1. I actually connect the output to the input, and then I go and then make it 0, right? And then you can imagine that this command has to be 1 only for a very small amount of time. I'm talking about picoseconds or something like that, right? Because if it's on for, like, I don't know, a few hundreds of nanoseconds, then, well, a bunch of outputs are going to pass through, right? It's not going to be 1 output. It almost feels like that it only has to be on for a moment, right? It shouldn't like be on for more than a moment. Or, well, we know a gatekeeper that works only at the moment and only samples the signal at only a single moment, and that gatekeeper is really a flip-flop. So a flip-flop connects the input to the output, a D flip-flop connects the input to the output only at the positive edge of the clock. So I can redraw this circuit by doing this. I'm going to bring my wires, but I'm going to connect them to a D flip-flop. It's actually a flipped or an inverted flip-flop, so the input is on the right, the output is on the left. Q and D and Q and the last one, right? And now I'm going to connect the outputs same way as before. Now, having these D flip-flops, and then I can connect their clocks all to the same clock signal. And that clock signal is really the command that we were talking about, right? So now at the positive edge of the clock signal, I take one sample and only one sample of the output and copy it to the input of the adder, the second input of the adder, right? At the positive edge of the clock. And that way I can actually make sure that if now using this clock thingy, I can actually make sure that I have a very good control on the timing of my counter, so I can count slow, fast, at whatever pace that I like based on the frequency of my clock. Okay, so now this is really a counter. So the lesson that we learned from this example is that we can actually, it's not the best counter, by the way. Like, I could make a counter using only these 4 flip-flops. I didn't really need the adder. So if somebody really loves to use adders, yeah, this is the way to go, but then, well, you're wasting a lot of resources. Now, the lesson we want to learn is that a lot of times we need both combinational, like the adder, and sequential circuits. We want to combine them in a system, and basically the system, what it does is that you actually take the outputs, which are these guys, or the current state of things. Right now the state, let's say the state of the output is 2, so like we are at the number 2, and then to go to the next number, right now we have to just add by 1. Imagine that I wanted to design a counter that only counts the odd numbers, goes from 1 to 3 to 5 to 7 and so on. So what happens is that all you need to do is to actually put a 2 here and start with a 1, like initialize with a 1, and then you're just jumping up with 2, right? So, and then that's just adder. Instead of this entire adder that they have here, I could have any kind of combinational logic, and we're going to see those kind of different kind of combinational logics in the next lecture. We're going to see that from this state to the next state, we can actually think about like what is the transition, what actually is enough kind of a condition, or enough what is enough for us to actually make a transition. So we look at the current state, and whenever the current state is a certain number or certain pattern of numbers, we know that okay, now I have to go to the next state, and then, well, to generate the next state again, the combinational logic is going to be helpful for us. So we're going to talk about that in the next lecture next week, but this was a nice segue, or basically to motivate you to watch that video as well. Thank you very much and have a great weekend.